Hello, this is Jack Jackson. In this video, we're going to start talking a little bit about volumes of solids of revolution. This one, we're going to work toward the washer method. So here we're going to actually introduce solids of revolution producing circular disk cross sections. So this would be the disk method. So one way to produce a solid with cross sections that are circles is to take a region in the XY plane and revolve it about a line in the XY plane. And this produces a solid of revolution. If the axis of revolution, the line we revolve around, is a boundary of the region, then this produces a solid with circular cross sections. Now, one way to physically produce such solids is by using a lathe. Think about taking a piece of wood and turning it into, say, a table leg. And basically, the person making the leg holds knives on the turning piece of wood and traces out some function across the top, and it cuts this into a surface of or a solid of revolution. So finding the volume of such a solid is found by taking slices perpendicular to the axis of revolution. And this will produce cross sections that are at least approximated well by circular disks. In order to see the connection between the graph of the function and the region in the XY plane and the solid of revolution, we'll make use of the following GeoGebra activity by Tim Brzezinski. And he does a lot of really good GeoGebra activities. And this one's called Disk Action, and there's a link to it. And I'll actually pull the app up here in just a minute and show it to you. In the app, we enter a function of x for f of x, the values for a and b. We do that over here on this window here. And so there's the formula. We'll give it a and b. You can change a and b by the sliders or by the little boxes. And it's going to graph the function here. Okay. And then, well, I'll show you in the thing in the app what actually happens, sort of a step at a time. So for now, let's suppose that the y values are actually y values of the function are actually positive, just for the moment, at least above the interval from a to b. And so if we integrate from a to b, we get an area between the curve and the x-axis. So anyway, so this is maybe 1 here, and this is 9 here on the x-axis. This region underneath this, we know would be what we get if we just integrate that. Now we want to take that region and rotate it, revolve it around the x-axis. Okay, and if we want to, so what happens if we just took a single line segment and revolve it? So let's take this single line segment here and create a rectangular region underneath. If you revolve that, you get a little cylinder, okay, a right circular cylinder. And what would be the volume of that? Well, the volume would be the area of the base times the height. The height is horizontal here. This distance across, well, from 1 to 9, that height, right now it's a height of 8, right? This distance across here. And so, but anyway, it's pi r squared times that height, because pi r squared is the area of that circle. So we want to break that apart into n equal intervals, equal width intervals, delta x being the same for each one, and then do this basically for each one. Okay, so let's take a look at the actual app for a second. So here's the app. There's the same function, 2 square root of x. And for right now, let's look at, let's take this all the way down to 1. Okay, and so we have one rectangle there. Here is a sort of a 3D perspective looking at an XY plane sitting out in space. And now we want to slide that. I think, is it this one? Okay, this one is just showing you that the radius is the height of this curve here, which we're taking it at the right end. and then the thickness is going to be some delta x, right? When we take a limit, that becomes dx. But, okay, we'll get to the limit in a minute. Now we want to take that and rotate it around that x-axis like that. Now in this case, we're going all the way to the x-axis, so this is a rectangle with one edge on the axis of rotation, of revolution. And so we do that. Well, what does that trace out? That traces out a cylinder. Okay, so you can think of it that way. Now, so now what we want to do is just like we did when we do a Riemann sum, we want to divide this up into smaller, or to some smaller pieces, let's say 4 pieces. And we're going to approximate the area under here by the area of these 4 rectangles. In this case, the way this particular app is set up, these are right Riemann sum approximations. So we approximate each rectangle here, the function with the horizontal line at the right end of each interval. So we have rectangles whose heights are found at the right end of the interval. Take each of those rectangles and now rotate those around, or revolve those around the x-axis, and you can see over here once again what's going to happen. We're rotating that around, and what does it trace? It traces discs. So you got circular discs. Okay, so now what do we do here? We actually, now again, this is the radius is the height at the right side here for one of these things. The width is delta x, which is the same for all of them. Now we want to get that approximation better and better and better, just like we got it better and better and better for the area here. We get closer and closer and closer to that area by letting n get bigger, and consequently delta x, which is just b minus a over n, gets smaller and smaller and smaller. And then it gets closer and closer and closer to the actual shape that we're wanting to do. Okay, so let's give it a whole bunch of these guys now and see what happens. So here are 50 of them. It's still an overestimate because this function is increasing. The right Riemann sum is making the area a little bit bigger here, which is going to make the volume a little bit bigger than what we're looking for here. But if we took the exact figure under here, the exact area, and then take that area, that region, and rotate it around once again, it's going to trace out the shape that we're looking for. Okay, so we can think of this approximation technique as just adding up these the volume of these various little disks. Each one of them is going to be a pi r squared times the thickness of delta x. Okay, so let's go back to our notes here. So what do we have? So there's another picture with 11 rectangles rotated around to give us 11 disks. So the thickness of each one of these is the height of the, called the height of the disk, which is its thickness. That's delta x, and it'll be b minus a over n for all of them. We'll make them the same size. And we take the x sub k at the right end of each interval. So the x sub k is a plus k delta x. It's exactly how we set up a right Riemann sum for just finding the area under here. But now, instead of just taking f of x sub k times delta x and adding those up for the Riemann sum, we're going to do pi times r squared times that thickness delta x. Now r is going to be the height of the thing here. So once again, let's see, if we put this, this one doesn't slide. If it's going to be height of one of these guys here, which is going to be the f of x sub k. That's the r, so we're going to square it. So there's your pi r squared delta x. And then we add all those up, we get an approximation of the volume we're looking for. So that is a Riemann sum. Now take the limit as n goes to infinity and delta x goes to 0. So increasing n gives us a better picture there. And taking the limit, this becomes an integral, right? It's basically the integral of pi r squared dx, where r is a function of x. So r is f of x. And the pi is a constant, so I brought that out front. So it's the integral from a to b of f of x squared dx and then times pi. So let's go ahead and figure out what it is for this particular one. It's 2 square root of x for f of x. So this is pretty simple to do. The volume is just the integral from a to b of pi r squared dx. Pi can be brought out front. A and to b is 1 to 9. Those are x values. R is the height of the function, which is just 2 square root of x. But then we want to square that. 2 squared is 4, which I can bring out front, so that's 4 pi out front. The square root of x squared is just x. And antiderivative would be 1/2 x squared, so there's x squared. Half of the 4 brings that down to 2 pi out front. Still leave the 2 pi out front. Evaluate this from 1 to 9, so that's 9 squared minus 1 squared. 9 squared is 81, 1 squared is 1. 81 minus 1 is 80, times 2 is 160, times the pi is 160 pi, which is the volume of the figure that we're looking for. And there's a decimal approximation for that. So let's review real fast. The basic idea is to see what the volume of a cylinder is when we take a little strip. The idea is to break this into sub-strips, just like we did in finding the area at the beginning of integration. Okay, we study that, rotate that around or revolve that around the x-axis. The shape it traces out are discs. The area of the volume of the disc is the area of the base times the height. Height is the thickness dx or delta x. And the area of the base is going to be a pi times r squared, and r is one of the y's here. So pi times y squared or pi times f of x squared. Add those up, we got an approximation. Take the limit as n goes to infinity, and we have a definite integral. And so that's the disk method. Notice a couple of key things. To get disks, what do we have to have? Let's look back at this picture here. We needed a rectangle, or all of the rectangles, to be touching the side of the axis of revolution, right? We're spinning this thing around the x-axis, as we saw over here, and that has to be actually touching the side of the rectangle that we're spinning. And of course, we're doing this for various rectangles, so we get various disks. So this is the disk method. We're going to see in the next video that the disk method can be generalized to something that we call a washer method, and we'll pick that up in our next video.